Okay, so I know this is a mixed crowd, so I prepared a presentation that has some introductory material. We can get right on to that. So we're going to be talking about density functional theory. I don't know how much everybody here knows about density functional theory. It was the subject of a Nobel Prize to Walter Kohn for developing density functional theory, and also that prize was shared by John Popo. So here was the award to Walter Kohn. Conventional calculation of the properties of molecules is based on a description of the motion of individual electrons, makes the methods complicated. Kohn showed that we don't need to consider each electron, we just need to consider the density of electrons at any point in space. And this leads to density functional theory. The simplicity of the method makes it possible to study large molecules or problems in geophysics and geochemistry. Today, for example, calculations can be used to explain enzymatic reactions or other complicated processes. It's taken 30 years for a large number of researchers to make it practical, but now the method is ready for wide application. So while it's an electronic structure method, why is electronic structure theory important to us in these problems? Because most of the information we want to know about chemistry and a lot of what we want to know about physics is in the electron density and the electronic energy. So the electron density directly gives us things like dipole moments, charge distributions, whether a material is ferroelectric. The electronic energy, according to the Born-Oppenheimer approximation, and that's Born and Oppenheimer there, gives us the potential energy surface. And then the gradient of the potential energy surface is the molecular force field from which we get geometries, lattice constants, bond energies, barrier heights, cohesive energies, spectra, most anything we want. So how do we calculate this electronic structure? So wave function theory, it's a bit of a retronym. People used to just say quantum chemistry, but now that we have density functional theory that doesn't deal with wave functions, we need a name for what's left behind. So that's wave function theory. So let's suppose we wanted to do the electronic structure of a small molecule, benzene. It has 42 electrons. Schrödinger says all the information is in the wave function, an antisymmetric function of 126 coordinates and 42 electron spin components. Hohenberg and Kohn theorem that underlies density functional theory says all the information is contained in the density, a simple function of 3 coordinates. So that's why the method is attractive. So when we do the calculation in wave function theory, we have to solve the Schrödinger equation, which is right there, h psi equals E psi. And the energy is the wave function, minimum over all possible wave functions, that minimizes this expectation value of the Hamiltonian, the average energy computed from the wave function. In density functional theory, we also do a minimization, but with respect to this much simpler function, the three-dimensional electron density, we minimize the kinetic energy of the electrons, the Coulomb energy of the electrons, and a functional of the density, which is called the exchange correlation functional, and it's a universal functional, and once we find that functional, we can solve this much simpler problem. So Paul Dirac, in a famous quotation, said in 1929 about this Schrödinger equation, we now have the equation that describes pretty much all of nature, at least at the chemical and physical level when you don't get to subatomic particles. The difficulty is only that the equation is very difficult to solve. And the problem with density functional theory is not that the equation is difficult to solve, but we don't even have an equation. So we have this unknown functional f, and we have to work on finding this functional. And we have various constraints and experience with what would make a good functional, but we don't have an exact equation for the functional, other than going back and saying that it has to yield the same results as the Schrödinger equation. So there are functionals that have achieved a lot of popularity. This is one that's achieved a lot of popularity in chemistry. It's called B3-LIP. That stands for Becky three-parameter Li-Yang par. It's a 3-parameter function. It depends how you count. Some people count more things as parameters. And you can see about 80% of the chemical literature is devoted to that one density functional. And then the rest of the literature, at least as of 2007, was divided among these other functionals. So B3-LIP is what's called a hybrid GGA, and we'd like to improve on it, so we're going to add more ingredients. So now the next slide will be about explaining those 2 lines. Okay, so what is a density functional a functional of? Okay, what you do is you represent the density by a single Slater determinant, which is a single anti-symmetrized product of orbitals, and then you solve a set of self-consistent equations for those orbitals. Now that sounds like a wave function, but actually it's just a parametrized representation of the accurate density. So you shouldn't interpret those orbitals too literally. The orbitals are introduced to give us the kinetic energy of the electrons, which is hard to get in a density functional that doesn't involve orbitals. So then from these orbitals, which are solutions to the Kohn-Sham equation, which involves the density functional, and therefore these orbitals are functionals of the electron density, we can compute from these orbitals the spin up and spin down electron density. We can compute the gradients of those two densities. And if our density functional just depends on the first line, we call it the local spin density approximation, Seperly-Alder approximation, Slater approximation for exchange. If you also involve the gradients, you call it the generalized gradient approximation. But that doesn't give good enough density functionals for most of chemistry, so one needs to add Hartree-Fock exchange. Now here's the Hartree-Fock exchange operator operating on an orbital. Notice that it's operating on orbital I. And notice that here we have a second coordinate, a coordinate of a virtual electron. This is electron 1, orbital I of electron 1. We need to integrate orbital I over all values of another coordinate. So that's called a non-local functional, so that makes things more complicated. Exchange is a non-local functional of the orbitals, which are functionals of the density, as I've mentioned. So when you do that, you get a hybrid GGA. B3-lip is a hybrid GGA. So now I've explained that. We make our density functionals also be functionals of the spin up and spin down kinetic energy density. Here's the way you would compute the kinetic energy density of an electron in an orbital phi j. So this is another functional of the orbitals, and when a density functional depends on that quantity, it's called a meta-functional. So our functionals are going to be hybrid meta GGAs, meta hybrid GGA. So how do we develop new functionals? Because this is one of the things we've been doing. Well, we look for new functional forms with the correct physics. Remember I pointed out that the density functional theory, you have the kinetic energy of the electrons, the Coulomb energy of the electrons, and then this exchange correlation functional. Now the Coulomb energy of the electrons, which for specialists is sometimes called the Hartree potential, but I like to think of it as the classical Coulomb interaction of that density of electrons. The problem with classical electrostatics is it doesn't recognize the discreteness of electrons. So when you have 10 to the 23rd electrons, it's not really a problem that when the density interacts with itself by Coulomb's law, you actually have 1 out of 10 to the 23 of those interactions as an electron interacting with itself. But in any molecular size system or geophysical size system, that's a very important approximation. So we have to get rid of this self-interaction, and that's one of the key things that the exchange correlation functional has to do. And Hartree-Fock exchange and this tau, which was the kinetic energy density, can do that. Because the kinetic energy density at a particular point in space can tell you whether you're in a 1 electron region of space or a many electron region of space. And if you're a 1 electron region, then you've got to turn off the Coulomb interaction, and you can do that. Okay, so then we're going to use this GGA exchange, depends on the spin densities and their gradients, and this kinetic energy density to try to control static correlation. So chemists divide correlation. So the real problem in getting accurate electronic structure is that the electrons avoid one another. And this is called electron correlation. Okay, there's two kinds of electron correlation. There's true electron correlation. If an electron's right here, another electron doesn't want to be right there. And if I just take a simple independent particle model, like most self-consistent field theories, they don't allow for that. They don't have one electron depending on the other electrons. All the electrons move in an average field. That's called dynamical correlation. Dynamically, when one electron goes here, the other one has a greater preference to be over there. Static correlation is a constraint on the nature of the wave function. It's sort of like you have H2 and you break the bond. One of the electrons wants to go with this nucleus, one of the electrons wants to go with that nucleus. That's actually harder to put into the theory than it sounds, but it's not really dynamical correlation. The electrons are far away. That's called static correlation. It's called near degeneracy correlation. Why is that? This hydrogen atom over here and this hydrogen atom over there, they have degenerate orbitals, orbitals that have about the same energy. So these are difficult problems, but and this is especially important if you're dealing with transition metals, as we do in so much geochemistry. So one of the things we tried to do is we tried to correct the problems with static correlation. And we found that this tau is very useful for that, this kinetic energy density. Once we've improved the exchange, we can improve the correlation. Exchange is a much bigger number than correlation. So if you have errors in exchange, as most density functionals have had, large errors in exchange, you can't really see the errors in the correlation. They're hidden. You have to unmask them. And then we have refined our density functionals for a wide variety of chemistry, main group chemistry and transition metals, data sensitive to medium range correlation energy, like barrier heights for chemical reactions, non-covalent interactions, and we have a large number of databases and a large number of data, and this leads us to new functionals, and our modern functionals we call Minnesota, like Minnesota 2006, Minnesota 2008. Okay, so here's a perspective on what we've accomplished. Let's consider chemical reactions. So we have a database for chemical reactions for main group compounds, and this is the mean error in that database. Now here's some various methods, and here's the computer time for a 16-atom example. You could also think of it as a 16-atom unit cell for a solid state calculation. So here's Hartree-Fock, that's the simplest wave function theory. Here's BLIP, that's one of the simpler density functional theories. So I normalized Hartree-Fock to be 1 unit of computer time. Density functional theory at a very simple level is even faster. Here's second-order perturbation theory and wave function theory. So we're starting to get more accurate barriers. Here's this famous B3-LIP functional, about the same cost as Hartree-Fock. Barriers are more accurate than Hartree-Fock, but 4 kcals per mole is still a lot. Here's a very expensive coupled cluster calculation from wave function theory, where you write down the wave function explicitly, many configurations. The barriers are starting to get good, but the cost is going way up. This is Poeppel's Gaussian 2 method, or G2 method. This was Poeppel's best method at the time that he won the Nobel Prize that he shared with Kohn. And he talked about this in his Nobel lecture. And the cost starts going way up, and he starts getting the barriers there. So here's what we've been able to accomplish with density functional theory with our Minnesota 2008. Our computer time is only twice as much as Hartree-Fock, so it's 700 times better than that, and we actually get better accuracy than you get from the state-of-the-art wave function theory. So we've passed up wave function theory for a number of problems. Furthermore, this calculation will scale as the 4th power of the number of atoms as you go to bigger systems than this, or bigger unit cells. This one here will scale as the 7th power. So it just gets better as you go to more complex systems. I talked about Hartree-Fock exchange. This is the percentage of Hartree-Fock exchange. BLIP has no Hartree-Fock exchange. That's one of the reasons it's less expensive. That does add to the cost. B3-LIP has Hartree-Fock exchange, 20%. MO8SO has 57% Hartree-Fock exchange. Now what happens is these properties here get better as you add Hartree-Fock exchange, but other properties get worse. So the question is, can you find a functional that works for everything? So here's transition metal chemistry, very important in geochemistry. So here's 2 bond energies, copper fluoride, copper's a transition metal, vanadium dimer, vanadium's a transition metal. So here's bond dissociation energies, here's best estimates of the accurate values, and here's some popular density functionals that are often used for this kind of problem. The B3-LIP, PBE0, TPSSH, and you can see they make huge errors in this bond energy. They make big errors in this energy here too, especially compared to what we had on the previous slide. So as we raise the fraction of Hartree-Fock exchange, these transition metals get worse. So the question is, can we find a functional that does well for main group chemistry? And so we could do silicon, magnesium, oxygen, very important, probably to people in this room, and also do transition metals. So we could do iron and other things that are important to people in this room. So can we fix this? Okay, so can a functional do well for main group bond energies, main group barrier heights for chemical reactions, non-covalent interactions, very important for adsorption, for example, and transition metal bond and reaction energies? Okay, we talked about B3-LIP. It's a popular hybrid GGA, 20% Hartree-Fock. Average error per bond over a reasonable data set, 0.9 kcals. Barriers, 4 kcals. Non-covalent interactions, 4 kcals. Transition metals, much bigger errors, 12 kcals. Here's actually a better hybrid GGA, even though due to inertia it's not as popular as this one. It has 27% Hartree-Fock. Not inertia of the physical system, inertia of users who don't keep up with the latest functionals. 27% Hartree-Fock. It does better for bonds. It does better for barriers. About the same for non-covalent interactions. But notice what happened. When we raised the fraction of Hartree-Fock to make these 2 numbers here better, transition metals got worse. Okay, so here is our MO6. That's our most general purpose functional that has no suffix, just Minnesota 2006, 27% Hartree-Fock. We do pretty well for bonds, we do pretty well for barriers, pretty well for non-covalent interactions, and we're starting to get transition metals down. So we feel this was the first functional that really had this uniform across-the-board agreement that you can apply to problems that have transition metals and main group chemistry, like something with iron, silicon, and oxygen. Sometimes, for very complicated problems, we want to get rid of Hartree-Fock exchange. That's the only reason we'd want to get rid of Hartree-Fock exchange. Here's a porphyrin fullerene system with 108 heavy atoms and 30 hydrogen atoms. If we run this calculation on this system with no Hartree-Fock exchange, it takes 17 hours of computer time. If we run it with B3-LIP or any of these methods up here that have exchange, it takes about 250 hours. So that's